In the next section, we're going to talk about integrations involving exponential and logarithmic functions. So for exponential and logarithmic functions, the rule is pretty straightforward that the exponential functions, the derivatives and the integration are exactly the same. For the logarithmic functions, the derivative of a ln function is going to be 1 over x. So the integration of x to the negative 1 power or 1 over x is going to be ln of x. One thing you do need to keep in mind, because of the domain issue, we do need to have the absolute value attached to whatever we're taking the ln to. There are other formulas, for example, integration of log base a or integration of ln. It's not really commonly used, so if you ever encounter to any of the problems, the best solution is to look at a formula. But those two are really commonly used. I do expect you to know those formulas or those two basic ones right away. So let's try some examples. There's really nothing to talk about it. So the first one, we want to find the integral, we want to integrate x squared e to the negative 2x cubed dx. So for this one, it's actually a nice way to combining section 1.5 and section 1.6. We see that we have a function e to the negative 2x to the cube power. And for this one, this is an inner and outer function. So this is a composition function where the inner is the power negative 2x cubed. The outer is e to a certain power. So let's let u equal to negative 2x to the cube. Then du is going to be negative 6x squared dx. We do not have negative 6, but we do have x squared dx. So we can divide everything by 6. So we got x squared dx is negative 1/6 du. Now let's change the problem, rewrite it. It becomes to integral of e to the u times negative 1/6 du. So let's put the negative 1/6 to the front. And because we're integrating e to the u's power, you just ignore that u is a function. Then according to the formula, this is just e to the u by itself. Rewrite it, which is e to the negative 2x cubed plus c. Okay. Now let's looking at another one. This one is really clear that we have an inner function, which is 3e to the x minus 2 raising to a power 2, which is the outer function. So we can let u equal to the inner function 3ex minus 2, then du equals to 3ex dx. This is the regular derivative. And du over 3 is equals to dx, e to the x dx, which is here. So we can rewrite it as 1/3 integral of u squared du. So to save some space, I just directly put put the 1/3 to the front, the constant to the front. Now we have a u squared, which is according to the power rule, which is 1/3 u to the third, 1 over 9 u cubed, which is 3ex minus 2 to the third power over 9 plus c. Next one, this is a definite integral. We want to integrate from 0 to 2 of e to the 2x dx. So it is really not too easy to see, but we still have an inner and outer. The inner is 2x, The outer is e to a certain power. So we're still going to do the u sub, let u equal to 2x. Then du is equals to 2dx, or dx is equal to 1/2 du. Now we still have the 0 and 2. So when x equal to 0, u, which is 2x, which is equal to 2 times 0, 0 still. When x equal to 2, u becomes to 2x, 2 times 2, which is 4. So putting everything together, we have 1/2 integral of from 0 to 4 e to the u du. Now e to the u, which is just going to be e to the u, evaluate it from 0 to 4, which is 1/2 e to the 4 minus e to the 0. E to the 0, which is going to be 1. E to the 4 is going to be some number, so we just leave it as e to the 4. So we ended up with e to the 4's power over 2. This is a number. E is approximately 2.72 something. So it's just similar to pi. So 2.7 raising to a power of 4. And we do not really know what is the actual decimal form, but that is fine. Now let's move on to the next one. Example 4, we want to find the integral of 1 over x plus 2 dx. Let's move this one a little bit low. So this one we have 1 over x plus 2. If you want, you can let u equal to x plus 2. Then you will end up with integral 1 over u. I'm not really calculating it, but hopefully you can see that either is 1 over u or its original form 1 over x plus 2. Because of x plus 2 is pretty straightforward, there's really nothing to think about it. What I mean is du is just going to be dx. So there's no extra terms. So if you already know it, according to the log formula, this is going to be just equal to ln of x plus 2 in the absolute value plus c. You can choose to do the u substitution, which is the more longer versions, or you can just see that 1 over x versus the 1 over x plus 2 are pretty much the same thing. So you can just directly apply the formula. Now we move on to the last problem. We can move this one up a little bit to have some more room to work on, which is a definite integral from 0 to pi over 2 of sine of x over 1 plus cosine of x dx. Because we have a fraction, normally speaking, we're going to let the denominator be our u. So you can see that u substitution is really commonly used and is really powerful method. As long as the problem is not that very straightforward, like a formula type of problems, probably 80% of chance you're going to use u substitution for the easier ones. For the harder ones, we're going to talk about it in the next chapter. So let u equal to 1 plus cosine of x. Then du is going to be negative sine of x dx, because the derivative of cosine of x is negative sine of x. Do we see? Sine of x dx. So we can rewrite the problem as negative, I can put a negative to the front, du over u, or if you prefer, 1 over u du. Then since this is a definite integral, we still have the zeros and the pi over 2. So when x equal to 0, u, which is 1 plus cosine of 0, is going to be 1 plus 1, which is 2. When x equal to pi over 2, u is 1 plus cosine of pi over 2, which is 1 plus 0, which is 1. So this one is another one, 2 on the bottom, 1 on the top. Now 1 over u, this is just going to be ln of u. And then we're going to evaluate it from 1 to 2, which is negative ln of 1 minus a negative, so plus ln of 2. ln of 1, which is 0. So we ended up with ln of 2. Because 2 is a positive number, so we can just get rid of the absolute value sign. Okay, so that's it for this section. The most important formulas or integration rules we need to remember, we need to practice a lot is the exponential and then the logs. And then you can see that a lot of the problems we are going to use the U substitutions. So the U substitution is really powerful, it's really commonly used, and that's probably the #1 popular method you are going to see. And combining with the U substitutions, you already see from both sections trig functions. And then we also need to evaluating trigs. Okay, so that concludes section 1.6. I will see you in the next video.